In this lecture, I want to talk about electrical shielding, which is what's used in what's called a Faraday cage, which is maybe something you've heard about or seen a demo of. And basically, the learning objective is to learn how the redistribution of electrical charge inside a conductor can shield not just the space inside a solid conductor, but the hollow spaces inside a conducting shell from an external electric field. Okay, so we're just basically going to go over some different scenarios here to help you understand how to analyze these types of problems with hollow charged conductors. And all of these conductors are going to be obviously drawn in 2D, so it's going to look like they're two-dimensional, but I want you to think about them as three-dimensional objects with a cavity carved out from the inside. Okay, so we're going to start out with this is going to be a charged one. Doesn't matter whether it's positive or negative. We're going to say it's a positively charged conductor. And again, I'm going to make it a weird shape, but it could be any shape, but this cavity is in the middle of a three-dimensional object. Okay, and I'm doing the thicker pen here so you can tell the difference between the actual conductor and some Gaussian surfaces I'm going to draw later. Okay, so the thick solid line here is the real conductor. Okay, and this is the cavity inside of it. So, okay, there's my conductor. For some reason, it seems satisfying to fill that in. Okay, so let's think about what's going to be true about the electric field of this charged conductor with a cavity. The first thing we want to think about is what happens to the charge itself within the conductor. So this is a conductor, so it's got positive and negative charges in it. Right now it's got an excess of positive charge, so it has fewer electrons than protons in a real material. Okay, and those charges are going to redistribute. In particular, the electrons are going to move, but you can think about it like the protons are moving. It doesn't really matter, but the charge is going to redistribute, so it's basically as far away from the like charges as possible, or those electrical forces are going to move the charges until the net electrical force on each of the charges is equal to 0. Okay, for a conductor like this with a cavity, that means that the electrical charges are going to move to the very outside wall. Okay, so in this case, I'm going to draw an excess of positive charge on the outside wall. Okay, and it's not necessarily going to be uniform, all right? If there are pointier bits or more curved bits like down here, you would expect to have a larger accumulation of charge than where the walls are quite flat, okay? And again, this has mostly to do with the fact that if you've got a pointy bit, that electrical force is actually going to mostly be pushing the charges up against the wall of the conductor rather than pushing them parallel to the wall and away from each other. Okay, so we know that just like in a normal conductor, even though this is hollow, okay, I know that charge will move to the outside, okay, wall. Not necessarily uniformly, okay? It can be uniform if the shape is uniform, but if it's not uniform like this shape, then it won't be uniform, okay? It depends on the shape. All right? Okay, what about the inside wall, okay? Well, the inside wall here, let's think about it by drawing a Gaussian surface inside my conductor, okay? Gaussian surface inside my conductor. So that's what that yellow line represents. And again, this is a 3D object, so really that Gaussian surface is going to be a three-dimensional surface. So I know that the electric field is still equal to 0 inside my conductor, okay? How do I know that? Well, That is always going to be true inside a conductor. Because the charge will always move to make it so. Okay, if the charge is free to move in response to electric field, it will, and it will move until that electric field is canceled out. Okay, so just remember that. The charge always redistributes in a conductor to make that electric field equal to zero because it can. So because of this, I know that Gauss's law tells me, so if you remember Gauss's law says that the flux through a closed surface is equal to the enclosed charge divided by epsilon naught. I know this is zero, okay, because E is zero. Okay, therefore my enclosed charge must be zero. Okay, so I know based on that there is no excess charge in this case on the inner wall. Okay, there may be charge inside here. There certainly is charge inside here, but there's an equal number of electrons and protons, so there's no net charge, no excess charge. Okay. For that same reason, inside the cavity here, inside the cavity, there's also no electric field because there's no excess charge to generate that electric field anywhere inside where I drew that yellow line. Okay, so inside the cavity, there's also no electric field. Okay, what's going on outside? Well, in this case, we've got a charged conductor. So there is a net charge on this conductor. That is going to produce an electric field outside of our conductor. And outside that electric field is going to be perpendicular to the surface. Right? And as we showed before, the strength is going to depend on the surface charge density. In fact, we can describe that electric field using the boundary conditions we talked about before, and we know the electric field is going to be equal to the charge density divided by epsilon naught in the n hat direction. That is, again, perpendicular to the surface. And I could draw a little Gaussian surface just like I did in the previous slide to prove that. Okay, so if I wanted to draw electric field lines, I would draw them coming out from the surface, perpendicular. For this shape, there'd be a few more at the pointier bits than there would be on the sides here that are pretty flat, but I didn't make anything too crazy pointy, so it's going to be pretty subtle. And again, this is just eyeballing it, not exact, just trying to get those field lines to be perpendicular to the surface wherever I draw them. Okay, and then because this is a positively charged surface, the electric field is going to point away from my conductor. And we end up with something that looks a little bit like a cell, in my opinion, okay? Or maybe like a little bacteria or something like that. All right. There's our first scenario. This is a positively charged conductor with a cavity. All right, let's do another scenario. Okay, for this one, we'll make this thicker again. This is going to be now it's neutral conductor with a cavity. So just like before, okay, except for this one's going to be charge neutral, and we're actually going to put it in an electric field. Maybe put that up here. Okay, so this is going to be in an electric field. All right, so I'm just going to randomly draw a shape here again. Maybe I'll make it look a little bit like that guitar pick, something like that, and make that a little bit thicker. Again, I'm drawing these walls pretty thick for drawing purposes, but the walls don't need to be thick for all these things to be true. I'm going to do that satisfying thing and color this guy in again. All right, here's our conductor. Again, now it's neutral, but it still has this cavity on the inside. Okay, and again, still three-dimensional. All right, the difference between this, what we did with the last one and this one is I'm going to go ahead, I'm going to scooch this over a little bit. I'm going to go ahead and put a positive charge right next to our conductor. I'll put it right there. Backwards. Right there. Okay. And now the question is, what's going to happen? So this positive charge certainly has its own electric field. Now this cavity, this conductor with this cavity is sitting in that electric field. What's going to happen? Well, the first thing that's going to happen is the charge in the conductor will still move to cancel that external field. Okay, and again, it's not because it wants to cancel the field. It's not anti-field. It's just that charge is going to move, just like you'd roll down like a ball would roll down a hill until it reached right the bottom or a saddle and it would stop. That charge is doing the same thing. It's moving until it reaches an equilibrium point and it stops. Okay, and at that point, there's no reason for it to move anymore. All right, so because of that, I can still draw this Gaussian surface inside my conductor. Okay, so this yellow line, that is a Gaussian surface. Okay, and I know that I still have that the electric field along that Gaussian surface is still equal to 0. Okay. Okay. That tells me that, again, the enclosed charge is equal to 0. And I can determine from that that inside my cavity, the electric field would still be equal to 0. Okay. So this is what a Faraday cage does. Okay. Even if I have a charge out here producing an electric field, a conductor or a conducting shell is going to shield the inside of that conductor from that electric field. So the book talks about being in a car or in an airplane. This is why they tell you to get in a car in a lightning storm. That car, because it's mostly made out of conducting material, metal, is going to shield the inside from that external electric field. Airplane does the same way. It's certainly not good for an airplane to fly through a thunderstorm or be struck by lightning. But if it does, actually, the inside of the airplane, because it's surrounded by a Faraday cage, and actually that's a part of the design, is shielded from that external electric field. And I will post a few interesting videos online. There's some really good Faraday cage demos. But like a simple one that we could do in class, if we were in classes, I could put an simple AM, FM radio. Radio waves are electromagnetic waves. It is an electric field. And I can put a cage, a conducting cage around that, and you would actually see that that signal would be either reduced or totally extinguished if it's a really good Faraday cage. So these are important to understand. Sometimes we're accidentally in a Faraday cage. Discovery Hall is a little bit of a Faraday cage. That's why we get such bad cell reception in it. But in some rooms, like laboratories that you guys might deal with in your future, sometimes you actually want to produce a lot of electromagnetic shielding. So a Faraday cage is built into the laboratory in order to shield any electromagnetic radiation from outside that could interfere with an experiment. Okay, so we know the electric field is 0 inside a cavity. It is shielded. The whole point of Faraday cages is that that you are shielded by the conductor. And this is what we know as a Faraday's cage. Okay, so let's think a little bit about the electric field outside of the conductor. The electric field is not zero outside of the conductor because there is some charge there, okay? There's certainly nothing that the conductor can do outside of it to cancel out the field. So we've got this positive charge, okay? The electric field is complicated. I'm going to try to draw it, but I'm probably not going to get it exactly right because it depends on the shape of the conductor. Okay, at least near the conductor, right? If this charge was really far from the conductor, certainly the conductor would not affect the charge, which would just be radially outward. But once we put this charge near the conductor actually modifies what the electric field looks like due to that charge. So what's going to happen is our charges inside this conductor, like I said, they're going to redistribute in order to cancel out that external field. So what that means is that we're going to get a bunch of negative charges here on the right-hand side of the conductor. So the electrons are going to flow from throughout the conductor to the right side because they are attracted to this positive charge. That's going to leave an excess of positive charge, okay, on the left-hand side of this conductor. Inside the conductor, right, if it was just these two sets of charge configurations, you would get an electric field that is directed to the right, which is the opposite of the electric field direction from this positive charge, which of course, if there was no conductor here, would be to the left. We don't get that electric field to the right because the electric field is zero, but when you think about how to draw these charges, you want to think about, okay, how could I draw them so they would produce an electric field that would be in the opposite direction and therefore cancel out this external field, okay? And again, how they redistribute is kind of complicated because they do whatever they need to do in order to cancel out that internal field. But in general, you're going to get more negative charge here on the right and more positive charge on the left. And when you put that into the electric field of this positive charge, that's going to change the electric field because it's going to come and connect to this conductor. Where it connects, it is going to, again, be perpendicular to the surface of our conductor. Okay, so I'm just going to draw a few field lines here. And it's going to look something like that. And of course, there's also going to be field that does not intercept with the conductor, and that's going to go around the edges. Okay, but this just generally gives you an idea of what it looks like. And again, overall, even though the charge is redistributed, this conductor is still electrically neutral. There is not an excess positive or negative charge, okay? So again, so our electric field is going to be complicated, okay? But it will be perpendicular to the surface, okay? And it's still going to be proportional, okay, to that charge density. I can still draw the Gaussian surface here to describe that electric field, and Gauss's law still has to hold. So I'm still going to get that same relationship for the electric field. This charge density is going to change as I go around the conductor, so the electric field magnitude will not be constant around the edge of the conductor. It's going to redistribute itself in order to cancel out that electric field. All right, let's do one more example. Okay, we're going to make it a little bit more interesting. Okay, now we're going to have a neutral conductor. And now the charge is going to move inside the cavity. All right, how'd it get in there? I don't know. All right, let's go ahead and draw that guy. I'm going to make this one a nice light color here. And again, just going for a random shape. I'm not really planning anything here. Okay, we'll make it I'm making fairly complicated shapes here. In your guys' homework assignment, you'll probably get some simpler shapes, and that's going to simplify things like how the charge redistributes. Okay, so keep that in mind, but I'm trying to keep this as general as possible in the lecture. There's our conductor. Again, inside we have a cavity, but now we're going to add some extra fun inside, and I'm going to put the positive charge here inside our cavity. Okay? So now what is going to happen? Okay? Now what's going to happen with the charge? Okay, so now, if I think about it, I'm still going to have zero electric field inside the actual body of the conductor. Okay, so now the charge, they will move to the inside wall, or the inside surface of the conductor. Again, because I drew a funky shape here, it's not going to necessarily be uniform. Okay? Again, it depends on the shape. If it is a uniform surface, though, it will be uniform, assuming the charge is right in the middle. If it's not right in the middle, it again gets more complicated. But basically, just like before, they move until E equals 0 inside the conductor. Not because they want to, because they literally don't have a choice. Okay, so inside the conductor, electric field is going to be equal to 0. So that means that if I draw that Gaussian surface again, this is a three-dimensional Gaussian surface that fits inside the conductor. Okay, the electric field is equal to 0. And again, this is along our Gaussian surface and really everywhere inside the conducting material, okay? And I'm trying to be a little bit careful here with words to not confuse you, okay? Because here, we'll just get to the point, actually inside the cavity, the electric field is not equal to 0, okay? The electric field is not equal to 0 inside the cavity because there's that positive charge there, and that positive charge is going to put an electric field in that free space inside the cavity, okay? However, if I think about this Gaussian surface here, okay, the electric field is still 0 along that Gaussian surface, so that still tells me, Gauss's law still tells me that if that electric field is 0 along the surface, if this is 0, then my enclosed charge has to also be 0, okay? So basically what that tells me is that the charge is going to redistribute, just like I said, it's going to go along the inner wall here, but now the amount of charge that redistributes itself along that inner wall is going to be just the right amount of charge to cancel out this positive charge here. Okay, so I'm going to get as much negative charge along this inner wall as I have positive charge here. So Q enclosed is going to be equal to 0 because Q enclosed is equal to our charge in the cavity plus our charge on inner surface. Okay, and that, when I add it together, is going to be equal to 0. Okay, so like I said, this inside the cavity, it's not going to be equal to 0 because there is still charge in there. Okay. Inside the cavity, the electric field is still perpendicular to the surface, okay? And you could still think about what would happen if I drew a little Gaussian surface like this and thought about what Gauss's law would tell me about how the electric field and the charge density are related again. Okay, I'll let you guys think about that. Okay, now let's think about what happens outside here. This was initially a neutral conductor. We had a lot of positive, or we got all our negative charges, or not all of it, some of our negative charge moving to the inside wall here to cancel out the positive charge to ensure that the electric field inside our conductor is equal to 0. That is going to leave an excess of positive charge on the outside of our conductor. So let me go ahead and draw those positive charges. I'm not being super precise here. Again, you want them to kind of accumulate in the curvier bits, maybe more spread out in the less curvier bits. Okay, so here's the surprising thing. On the outside of the conductor, okay, so outside, there will be an electric field due to that surface charge, that positive surface charge, okay. It is still going to be perpendicular to the surface, and it will depend on the surface charge on the outer wall. What perhaps is most surprising is that the surface charge does not depend on the placement of Q, of plus Q, except in magnitude. Okay, so by that I mean the amount of surface charge here you get of excess positive surface charge is actually going to be equal to the amount of positive charge I put in the middle. Okay, and that's because I drew in an equal amount of charge to the inner surface. So the total charge will be equal to Q. But how that charge is distributed doesn't depend at all on where Q is inside the cavity. Okay, where I put Q inside the cavity is going to change how this inner surface charge is distributed to cancel out that electric field inside the conductor. But this positive charge, there's no way it can know where Q is, because as far as it knows, there is no electric field inside the conductor. As far as it knows, this whole thing could be filled in, right? These are just charges, they're not smart. Okay, so the fact that the electric field is 0 inside the conductor means we get a loss of information in terms of where this positive charge is to the outside wall. Okay, so where these positive charge distributes on the outside wall is just like it would distribute if this whole conductor was charged with a charge of plus Q. It's still going to accumulate at the curvier bits and be less dense at the straighter bits. Okay, and just like before, we're going to get an electric field that is perpendicular to our surface, right, and proportional to that surface charge density. Okay, so I'm just going to really quickly eyeball this. You guys can do it prettier in your own notes if you want. All right, but there we go. We're going to get a few more here. Curvier bit, spaced out a little bit more. All right, so that's what the electric field is going to look like on the outside. The electric field inside is going to be, again, a little bit trickier to draw, but it's still going to end up being perpendicular to the wall everywhere. Okay, and I'm not going to draw all the field lines. Just give you an idea here. That's not very perpendicular. Let's see. I'm trying to make it so, again, when the field lines hit the wall, ends up being perpendicular, something like that. Okay, and inside that gray area, again, the electric field is going to be equal to 0. Okay, the next thing I'm going to show you guys is a little simulation that does this for a square, a cube really, okay? But I just want you guys to keep in mind when you do your homework that things get simpler in terms of trying to draw, in some ways, not totally simple, but simpler when you're thinking about some of these concepts. When the conductor is a sphere with a cavity. Because then we don't get a change in shape necessarily, at least on the outside here, changing the surface charge density.